Hi, welcome to Probabilities. How may I take your order?
Yeah, could I get the half chance meal and the 7 chance meal, please?
And if you don't get both, would you like to make them mutually exclusive for the Children's Hospital?
Yeah, sure, whatever.
Sure, so there's a 1 in 14 chance you'll get both meals and a 9 in 14 chance that you'll get one. Are you good with that?
Yeah, I guess, sure.
That'll be 1869.
Hello, everybody, and welcome back to another episode of Beau Maths. In the last couple of videos, we've been talking about proportions of chance, namely probabilities. How we can use math to talk about, well, chance, randomness. Is it going to happen? Is it not going to happen? What's the likelihood of it? And to be honest, I was partway through filming an epic Minecraft video that deals with some cool probabilities until I realized, oh man, we still didn't talk about some really important ideas, namely how to combine probabilities. And so that's what we're going to be doing today, and then afterwards we will get to the Minecraft video, because I know a lot of you are subscribed for those. The idea. So the idea with combining probabilities is, what if we want to find out the chance of multiple different things, right? For example, what's the outcome I roll a 3 on a dice and I get heads on a coin? Not just the probability of the dice, or not just the probability of the coin, but the probability of both of those things happening. Or I could have something like, what's the chance I play badminton on Tuesday or on Thursday, right? So that's using the idea of or. So maybe it could be one, could be the other, or it could be both, right? Each with their own respective probabilities, but how do I somehow combine those? So that's kind of what we're going to be looking at today. And before we kind of get into the details, I want to quickly talk about what does it mean to have and versus or, just to clarify. And versus or. It might seem like kind of a silly idea at first, like, oh well, and or, I mean, I use them all the time in English, why do I need to define them? But it's important that we're all on the same page when it comes to these two things. So with and, this is that both events must happen. So for example, I eat and I sleep. I must both eat and sleep for this to be a true statement. I can't just have one or the other. All right, so that's pretty self-explanatory. Or is maybe a little more worthwhile talking about. This is either event or both could happen. So sometimes when people say or, it's like one or the other, but not necessarily both. Like, for example, you can either watch this show or watch that show. If they're on at the same time, you can only do one of the two. You can't do both, right? So that would be what we would call an exclusive or. So an exclusive or doesn't include the or both. But usually in math, when we're just talking about a regular or, it means either or both could happen. So if I eat or I sleep, that could mean I can eat and not sleep, or I can sleep but not eat, or I can do both eating and sleeping. The only thing I can't do is not eat and not sleep, because none of these conditions would be satisfied. So that's what we mean by an and an or within mathematics. Now that we've clarified that, let's start talking about how to kind of construct what it would look like combining probabilities, either using and or by using or. And to start with, we're going to look at an idea called possible outcomes. Possible outcomes. So we've already kind of discussed the idea of possible outcomes with probability, right? For example, if you want to figure out the chance of rolling a 1 on a d6, a 6-sided die, well, the possible outcomes are 6, and the total ways to get a 1 is just 1, so your probability would be 1 out of 6. So this possible outcomes idea is already familiar to us. But what if we have a more complex situation? So let me paint a picture for you. All right, so let's say I'm at a restaurant and there are 3 appetizers, fries, salad, or bread, 2 entrees, salmon and pasta, and 2 desserts, cake or pie. So how many possible outcomes are there? And this is if we can only choose one of each. Yeah, so how many outcomes? How many possible meals could we have? It's made up of 1 appetizer, 1 entree, and 1 dessert. Well, the way we can do this is by using what's called a tree diagram. And we can start by listing our possible appetizers. And then let's say I chose fries. Well, after I chose fries, I could still either choose salmon or pasta, right? Similarly, if I chose salad, I would still have these two options available, right? And likewise with bread. And then what about the two desserts? We have cake and pie. So let's say I chose fries and then salmon, I still have the choice of either cake or pie. Similarly, any one of these routes I choose, I still have this kind of choice between cake and pie for my dessert. So each one of these paths kind of represents a different possible route I could take from one of my choices, right? I could choose salad, then pasta, then cake. Or I could choose bread, then salmon, then pie, right? So each one of these routes are one of my different possibilities, and these are all of the different possible meals I could have. And how many meals do we have in total? Well, if we count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different meals. Okay, so this is a nice visualization of how many possible outcomes there are. However, is there a faster way we could have done this? Because that was a lot of work writing that out. And imagine if there were way more options. I mean, this is a pretty garbage restaurant if this is the only options you have. So is there a way we could do this a little more mathematically? Well, what did we do? We basically had 3 possible groups, right? Fries, salad, or bread. And then in those groups, we had 2 more possible groups, right? Salmon or pasta. And within those groups, we had 2 more possible groups. So what is this thing in math where we're doing groups of groups of groups? What's that idea correspond to? That's multiplication, right? If I had 2 groups of 5, that's 2 times 5. Or 3 groups of 7, that's 3 times 7. But now I'm just doing a group of a group of a group. So if I had 3 groups of 2 groups of 2, right? 3 groups of 2 groups of 2, then I just multiply those 3 numbers, 3 times 2 times 2, which is going to be 6 times 2, which is 12. And that's exactly what we counted right there. So when you have a situation like this, the way to get the possible outcomes is just to multiply kind of each of these segments, right? What if I wanted to consider something like, I want to figure out what's the probability that I choose one of these meals. So what would be the probability that I get salad, salmon, and then pie? Well, that's basically one of the paths out of the 12 possible outcomes, right? So the probability I choose, let's say, salmon, pasta, pie, that is going to be one of those routes out of the 12 possibilities, right? But here's another way we could look at it. What's the probability I choose the salad out of these 3 appetizers? Well, that's 1 in 3, right? So this is the chance that I choose the salad. And then what's the chance I choose the pasta? Well, out of 2 different entrees, one of them is pasta. So this would be the chance I choose the pasta. And what's the chance I choose the pie? Well, again, there's 2 options for the dessert, and only one of them is pie, so I have a 1 in 2 chance I choose the pie. Now, how can these 3 be combined to get 1 over 12? These can be combined through fraction multiplication, right? Because notice, 1 times 1 times 1 in the numerator is 1. 3 times 2 times 2 in the denominator, that's right. That's the possible outcomes that we just calculated there. That's 12, and that gives us exactly what we see right there. So this is the probability we choose a salad and a pasta and a pie. So it might start looking like this is how we should combine probabilities when we're anding them together, when it's the probability of one event and another event. And indeed, it is going to be multiplication. However, what we need to do first is we need to talk about kind of a little caveat on this idea, and that's the idea of independent and dependent events.
Independent and dependent events.
So 2 events are said to be independent if neither influences the other's probability. So, for example, let's say I roll a dice and then I flip a coin. Does me rolling the dice have any impact on what the coin's result is? Or does the coin's result have any impact on the dice's result? No, it doesn't. So that would be an example of independent events. So something that's not independent would be a dependent event. Okay, so 2 events are dependent if one influences the other's probability. So what would be an example of a dependent event? Well, if you recall from the exercise video in the last video that we did, Aiden was basically drawing a card from a deck to see if it was an ace, and then he didn't put it back and he drew another card and he just kept doing this over and over again. That would be an example of dependent events, because when he draws a card and doesn't put it back in the event, that influences the probability of his next draw, right? Because it's out of less cards, and depending on what he actually drew, that influences what is actually in the deck still, right? So that would be an example of dependent events. Right? So we could have drawing a card and then not replacing it before drawing another card. So now that we have that in mind, now we can actually talk about how to basically combine probabilities through AND.
Combining probabilities through AND.
So if I want to find the probability of one event occurring and another event occurring, I just have to multiply the events. That's what we kind of thought might happen over here, right? Where we just take their probabilities, and if we multiply them, we see that the total that we get in the denominator kind of corresponds to doing this process here of taking kind of all of these different possible routes. And then the numerator is going to be kind of a similar thing, except it's basically going to correspond to our chances of selecting kind of one of those parts of any of those routes that we actually choose. The only caveat is that these events need to be independent of each other. If they're dependent of each other, then the first event can influence the second event's probability. Then it's not just as simple as multiplying them anymore, because the second event's probability will be changed, right? Because the first event influenced it. So that gets into much more complicated math, which we're not going to deal with in this series. We will someday. But for the time being, we're just going to assume that these are independent events. So anything I give you, it's always going to be an independent event situation for this series. So if two events are independent, the probability of them both occurring will be the product of their probabilities. So for example, what's the probability I flip a coin and get heads, and then I roll a dice that's a d6, so a 6-sided dice, and I get a prime number? What's the probability of getting heads on a coin? Well, that is going to be 1 in 2, right? There's two outcomes, one of those is a head. And for the d6, what's the probability of getting a prime number? Well, what are the different prime numbers between 1 and 6? We have 2, 3, and 5. And remember that 1 is not a prime number. So we have 3 different outcomes out of the 6 that satisfy this property here. And 3 out of 6 is a half. So both of these actually have a probability of a half. But we want to know what's the probability of getting heads and getting that prime number. So now that full probability, we actually have to multiply these two probabilities, a half times a half, and we get a quarter. So there's a 1 in 4 chance that we flip the coin and also get a prime number on the d6. All right, so just remember, ANDing is multiplication, assuming the events are independent. So now let's go on to OR. What does it mean to OR two different probabilities? So to talk about that, we first need to discuss the idea of mutually exclusive events.
Mutually exclusive events.
So two events are said to be mutually exclusive. Sometimes that's also called disjoint. So two events are called mutually exclusive if they cannot both occur at the same time. So what would be an example of that? Well, can I roll a 1 on a dice and also roll a 2 on a dice at the same time? No, right? They're mutually exclusive events. They both can't occur. So an example of something that wouldn't be mutually exclusive. What about rolling a 1 on a die or rolling an odd number on a die? Those events could both happen, right? Because if you roll a 1, well, that's an odd number, right? So those wouldn't be mutually exclusive events. Now, in the last video, we talked about complements, right? So complement was basically the opposite event. So since it's the opposite event, it can't also occur with the event it was a complement to, right? For example, a heads is complement to tails. So complements are always mutually exclusive to the original event. All right, so now that we have the idea of mutually exclusive events, kind of like with AND, we needed kind of the condition of independent events, we're also going to need this condition of mutually exclusive events for our OR probabilities. So now let's actually talk about that.
Combining probabilities through OR.
All right, so let's consider two mutually exclusive events. Heads or tails, that's a pretty standard one. So we know the probability of getting heads is a half, right? And we know the probability of getting tails is also a half. What happens if we look at a half plus a half? Well, heads would fill in half of the whole, and tails would fill in the other half of the whole. And in total, well, a half plus a half, that gives us 1, or 100%. And one way we can interpret this is that, well, it should make sense that we get 100% because all of the possibilities for flipping a coin is either heads or tails. So heads and tails, they completely encompass all the possibilities for getting this 100%. So when we do 1/2 and then we add the other half, that essentially has us putting together all the possibilities to give us the total. And if the total is 100%, then we know that all the possibilities are accounted for. In a more complex situation, let's say I roll a dice, and let's say the two things I look at are rolling a 1 or rolling an even number. So for rolling a 1, I know there's a 1 in 6 chance, right? We're assuming this is a d6 dice. And rolling an even number, I know that there's a half chance, or a 1 in 2 chance, right? There's a half amount of even numbers in a d6. So that means then that if we consider all of the possibilities, right? So all the possibilities is basically 1, 2, 3, 4, 5, or 6, right? So this is the 100%, the total. Then the 1/6 from the 1, that kind of contributes to this piece of all of the outcomes, right? All of the outcomes being this full rectangle of 1, or 100%. And rolling this even number, that contributes to adding basically a half to the rectangle. So we can think about this half right there. But notice we haven't completely filled the rectangle, and that's because there's still a couple possibilities that are missing, right? We technically could get a 3 or a 5, right? Because those aren't encompassed by either of these, right? Neither of them are a 1 and neither of them are even. But we have filled in some of the area here, right? And so since these events are completely disjoint from each other, their areas comprise of different events that are in this total here. And so we can just add their areas, 1/6 plus 1/2, and that will give us basically the probability of getting 1 or an even number, basically the probability of being in the blue or in the purple area. So a half plus a 6, well, we just need to make a common denominator. So we get 1/6 plus 3/6, which is 4/6, which simplifies to 2/3. So the probability of rolling a 1 or rolling an even number would be 2/3. Similarly, the probability of rolling heads or tails would be 100% because it's guaranteed to be one or the other. And so from this, hopefully you've gotten that to combine probabilities with or, we add them, not multiply. So anding was multiplication and using or was addition. But we need to add in this condition of mutually exclusive. Why is that the case? Well, what if I consider something like roll a 1 or roll an odd number? So these are not mutually exclusive events, whereas these two were mutually exclusive. If I considered this, well, yes, this has a probability of 1/6 and this has a probability of a half. However, inside of the 1/2, so the odd numbers are 1, 3, and 5, right, between 1 and 6. The probability of getting the 1 is also going to be included in that space, right? And so now if we added up these probabilities, that would be too much, right? Because we're basically accounting for the 1 too many times. We're accounting for it with the probability of the odd number, and we're accounting for it with the probability of getting a 1. So because of that, the fact that they're not mutually exclusive screws up the ability for us to just add these probabilities and actually get the real probability. Now that we know why we need mutually exclusiveness, we can kind of write the rule. So if two events are mutually exclusive, so they can't both occur at the same time, the probability of one or the other event occurring will be the sum of their probabilities. So what's the probability of rolling a 4 or a multiple of 5 on a d20? So first of all, let's consider what's the probability of rolling a 4. Well, that is 1 out of 20, right? And what's the probability? So this is the probability of rolling a 4, because there's only one 4 out of the 20 possible sides on that dice. And for a multiple of 5, well, we know that we have 5, 10, 15, 20. There are 4 different multiples of 5 between 1 and 20 out of the 20 possible outcomes. We don't need it to be both, and in fact, it can't be both because 4 is mutually exclusive from a multiple of 5 because 4 is not a multiple of 5. So that means to find the probability of rolling a 4 or finding a multiple of 5, we can simply add these probabilities and we get 5 out of 20, which simplifies to 1 over 4 or 25%. So there's a 25% chance of either rolling a 4 or getting a multiple of 5 on a 20-sided dice.
Concluding thoughts.
Alright, so I hope you found that video useful, and I hope you're starting to see just how deep probability can actually start going. We can figure out the probability of these more complex compound events by looking at what's the probability of ANDing two things, or the probability of one event or another event occurring. We need to make sure that we understand the conditions for these ideas for being able to just add or being able to just multiply. We need to make sure to look at adding that the events need to be mutually exclusive, and we need to make sure that for multiplication the events need to be completely independent of each other. But that's going to do it for me today. Thanks for watching as always. You have a good one, you stay groovy, and I'll see you in the next video.
Okay, let's give this one last shot. Screw it, I'm watching Beau Maths.